one-way analysis of variance, which is known as ANOVA. Analysis of variance and t-test, they are almost the same thing. The only difference is that t-test can only be done on 2 samples of a population, whereby analysis of variance can handle more than 2. So it means if you're considering more than 2 samples of a population, we have to use analysis of variance. Then analysis of variance, these are the 3 formula that is needed. Number 1, we have variation between. These are things we need to calculate. Variation between. We also need variation within. Variation within. And we also need total variation. That is, we need this in order to get the analysis of variance table. Now, variation between, let's say between treatment, the formula is given us. We have a B summation xg dot minus x bar all raised to the power of 2. This is a formula to get the variation between treatment. And variation within treatment, you can use this formula. We say summation into bracket x j dot k minus x bar j dot then all square. So this is the formula to get variation within treatment. And total variation, that is we have a summation x j dot k minus x bar all square. So this will give us total variation of the treatment. Now, assuming we have let's say we have 3 treatments, says x, y, z. So let's say we have x1, x2, x3, x4, x5, y1, y2, y3, y4, y5. Then we have z1, z2, z3, z4, z5. Now, if you look at this now, this is the first treatment. We have treatment 1, treatment 2, treatment 3. So which means we have 3 treatments. So which means in this case, our A equals to 3. A stands for the number of treatments in the table. Now, each treatment here has 5 observations each. So that is our B. B is the number of observation in each treatment. So the number of observation in each treatment, we have x 1, 2, 3, 4, 5. So we have 5 observation. So in this case now, this B now, this stands for 5 here. Then in the case where we need A, our A will be equals to 3. So it means A stands for number of treatment, while B stands for number of observation in each treatment. And in this case now, we are using equal observation for all the treatment. So this now we're going to use this to get our ANOVA table. So this is how the table look like. You can see the first column here we have variation. Now we have here between treatment. This is the variation between treatment, denoted with V subscript B, and we have this formula B summation into bracket xj dot minus x bar raised to the power of 2. Xj dot. What is xj dot here? This is x now stand for the treatment. X stand for the treatment here. Okay, let's move on. We have raised to the power of 2. Then we have variation within treatment. Variation within treatment, we can use the formula I previously wrote down to get the variation within treatment, or we subtract the total variation, or we subtract variation between treatment from the total variation, and that is going to give us the variation within treatment. And we have the total variation with this formula xj dot k minus x bar all raised to the power 2. So this is denoted with V subscript t. Now, the second column here is talking about the degree of freedom. The degree of freedom for between treatment, we have A minus 1. That is the degree of freedom, A minus 1. Our A stands for the number of treatment, total number of treatment. Here, so we have A into bracket B minus 1, whereby B stands for the number of observation in each treatment, Now, for total variation, we have AB minus 1. Now, the third column here is talking about the mean square. Mean square for within treatment, between treatment, and mean square for within treatment. So if we divide these two, that is SB, S squared B divided by S squared W, that's going to give us F calculated. Let me put it here. Calculated F. Then, what is the main thing here? The main thing here is the last column here, F. We need this F in order to compare, what's it called? F tabulated on F table using maybe 0.05 level of significance or 0.01 level of significance. Now that we know this, so we are going to use this table now to examine the so, three different kinds of fertilizer tested on 3 groups of corn for 4 weeks. This is 4. Sorry about that. The objective is to check the difference in mean growth of the corn per week. Apply one way ANOVA using a 0.05 significance level. So now, how many fertilizer here? 3. That is 3 treatments. 3 treatments. And how many weeks? 4 weeks. That is observation. So which means this fertilizer was observed for 4 weeks. And here we have X, Y, Z. This is the treatment. We have 3 treatments. And we have a 1, 2, 3, 4. Each has a 4 number of observation. So first of all, we say A. Our A here is equals to 3. Then comma. Our B equals to 4. A, number of treatments. B, number of observation in each treatment. But in this case, we have equal number of observation. So what do? N equals to A times B. That is, if you want to know all the total number of observation here, so you just have to multiply this A multiplied by B, and that will give us 12. If you count it one by one, everything should give us 12. Okay. So the first thing we do, this is the first step, hypothesis. We need to state the hypothesis. And what is the hypothesis here? Say apply one way ANOVA. The objective is to check the difference in mean growth of the corn. Just say for H naught, we can just say the treatments are all equal. Or we say there is no significant difference. Significance difference and the mean of the three treatments. Just say 3 fertilizer instead of treatment. 3 fertilizer versus H1, which is the alternative hypothesis. The alternative hypothesis is going to be hypothesis. There is a significant difference in the mean of the 3 fertilizer. So that is step 1. Step 1, we're able to state the hypothesis. Then 2, level of significance. Let's say alpha, level of significance. According to this question now, we are told to use 0.05. So we have 0.05 level of significance. Then 3, step 3, what do? Then we go into calculation proper. We go into calculation proper. Now, the first thing, according to this formula here, you can see we have x bar, and we also have xj.k, and we have xj dot. So now, the first thing we do is to look for x bar. So the x bar now is the mean of all the observations in the whole treatment. The mean of observations in the whole treatment. So we are going to add everything together, starting from here. So 3 plus 4 plus 5 plus 5 plus 4 plus 2 plus 3 plus 3 plus 6 plus 4 plus another 4 plus 5, all divided by our total number of observation is 12. So we have 12. Therefore, our x bar equals to, if you add all of this together, we're going to have 48 divided by 12. And 48 divided by 12 will give us 4. So it means the mean of all the observation is 4. So we have our x bar to be 4. Alright. So now we want to apply this formula for the total variation. We have xj.k. Xj.k here means for each variable here minus x bar. So each value here, we're going to subtract it from this x bar, then we square each. We have a v, there's a v total. The formula is giving us summation xj.k minus x bar square. Now xj.k means each value here minus the mean, which is 4. Then we are going to square everything. So what do we get? Start from, we have a 3. This is equals to 3 minus 4 square plus 4 minus 4 square plus 5 minus 4 square plus 5 minus 4 square plus 4 minus 4 square plus 2 minus 4 square plus 3 minus 4, rather 3 minus 4 square. We're using the x bar, which is mean, then plus another 3 minus 4 square plus, then we'll come to the third row here. We have a 6, 4, 4, and 5. So we have a 6 minus 4 square plus 4 minus 4 square plus another 4 minus 4 square plus we have a 5 minus 4 square. So if we add all of this together, this is 1, 0, 1, 1, 0. This is 4, 1, 1, 4. This is 0, this is 0, and this is 1. When you add everything together, therefore V total will be equals to 14. Our V total will be equals to 14. Okay, so let's go back to the table. Our V total here equals to 14. Let's just fix 14 into the table. Now we need between treatment, variation between treatment. There is a V subscript B, and the formula we have B summation into brackets xj dot minus x bar all square, xj dot minus x bar all square. So first of all, we need xj dot bars, rather not just xj dot bar. There is bar here. So what do we do now? We'll find the mean of each treatment. Then after finding the mean of each treatment, we're now going to subtract mean of each treatment from the main mean, which is 4. This is the main mean, or we call it grand mean. So now let's say x bar 1 is for the first treatment here. We'll find the mean. Say 3 plus 4 plus 5 plus 5 plus 5 plus 5 divided by, we have 4, because we have 4 observation here. So this is equals to, this will give us 4.25. X bar 2 stand for the mean of the second treatment. So also find the mean for the second treatment. We have 4 plus 2 plus 3 plus 3 divided by 4. This will be equals to 3. So the mean for the second treatment is 3. And finally we have x bar 3 equals to 6 plus 4 plus 4 plus 5 divided by 3. This is equals to 4.75. So the mean for the first treatment is 4.25. The mean for the second treatment is 3. And we have the mean for the third treatment, which is 4.75. So each value here stands for x bar g dot, j dot, j treatment 1, j treatment 2, j treatment 3. So each of this value now, we are now going to subtract it from x bar. And what is our x bar? Our x bar equals to 4. Okay, so it's variation between equals to, we should not forget that first of all, from the formula we have b here, and our b right from here equals to 4. So we have 4 into brackets x bar j, the first mean, which is 4.25 minus 4. So here we have 4.25 minus 4 all square plus the second mean, which is 3. We have a 3 minus 4.25. We have 3 minus 4 square plus the last mean, which is 4.75. So here we have 4.75 minus 4 square. Then we close the bracket. Now VB subscript B equals to 4 into bracket 4.25 minus 4 all raised to power 2 will give you 0.0625 plus 3 minus 4 square will give us 1 plus 4.75 minus 4 square will be 0.5625. So now V subscript B equals to, if you add all of this together, add them together, we're going to have 6.5. If you add these 3 together and multiply the 4, we're going to have 6.5. So we have our VB to be 6.5. Now variation within treatment. within treatment. So this is V subscript W. We can get variation within treatment using this formula, that is subtract the total variation, or it subtract variation between from the total variation. So that is a V minus V subscript B. V minus V subscript B. Now before we move on, we have 6.5 for VB here. Let's slot it in. VB equals to 6.5. 6.5. Let's be forming the table one after the other. Now V the subscript W equals to V total. Our V total, which is equals to 14. So we have a 14 minus VB, which is 6.5. So we have 6.5. VW equals to 14 minus 6.5. That is 7.5. So here now we have a V within equals to 7.5. So before we move on, before we go to the this is a step 1, 2, 3. This is the end of step 3 here. So before we move to step 4, let's go back to this table and finalize it. So what do we have here? So our A has been defined to be the number of treatment, and in this case we're treating 3 treatments. So here we're going to have a 3 minus 1. Therefore our A equals to 2. A is 3 into bracket. Our B is number of observation in each treatment, and the number of observation in each treatment here is 4. So therefore we have 4 minus 1. 4 minus 1 is 3. 3 times 3, this is 9. AB minus 1, that is 3 times 4 minus 1. 3 times 4 is 12 minus 1, you have 11. So what do we do here? When you add 2 plus 9, you have 11. 6.5 plus 7.5, you give it 14. If you are not getting it that way, that means you are doing something wrong. Now, the mean square for variation between treatment, how do we get that? We have V subscript B here, and this is our V subscript B, which is 6.5. So what do we do here? We have 6.5 divided by A minus 1, and our A minus 1 is 2. So therefore, this mean square for variation between treatment, if you divide 6.5 by 2, we're going to have a, so that is 3.25. Now for this, V subscript W 7.5. So we have it as 7.5 divided by degree of freedom here, which is 9. So therefore we have 0.8333. Now if you come to the F calculated here, we have mean square for variation between, which is 3.25 divided by variation within treatment, which is 0.8333. So this will give 3.9 with degree of freedom 2.9. Where do we get this 2.9? We have degree of freedom 2, and we also have degree of freedom 9. So we cannot use degree of freedom 11 because 2 plus 9 will definitely give us 11. So this is our F calculated, which is 3.9. So this is how to form ANOVA table. So let's move on from where we stop. So our F calculated now, F calculated equals to 3.9. So right from here now, we're going to move to step 4. Step 4, what are we going to do? Decision making. So how do we make the decision here? We just say if F calculated is greater than F table, there's a F tabulated at 2.9 of 0.05 level of significance, then what do we do? Now hypothesis of equal means can be rejected. What do we do? Reject H naught, which is a null hypothesis. If F calculated is greater than F tab, what do? We reject the null hypothesis. Now our F calculated is 3.9, so now we need to get F tabulated at 2.9 level of significance. So this is F table right here. This is F table. You can see we have number at the top horizontal, and we have number at vertical. So the horizontal number denotes degree of freedom for between treatment, and here we have degree of freedom within treatment. So the degree of freedom we are considering here is 2.9. So we look for 2 here. This is 2 here. Then we'll come here, we look for 9. This is 9 here. Where do they intersect? They intersect at 4.26. You can see 4.26. So which means our F table is 4.26. F table at 2,9, 0.05, 11 of significance. We have 4.26. You can see we have 5% significance level here. So now comparing this, now we can now see that our F calculated, which is 3.9, is less than our F tab, which is 4.26. Therefore, we cannot reject H naught. What do we do here? We cannot reject H naught, or we say, let's say, we do not reject the null hypothesis. We do not reject the null hypothesis. We do not reject the null hypothesis. Then step 5, conclusion. How do we conclude? We say, since F calculated is less than F tabulated, or you say since, or since we do not reject the null hypothesis, therefore we conclude that the mean of the three fertilizers are all equal. The mean of the three fertilizers are all equal. So this is our null. This is our conclusion. You can see we break it down step by step. Step 1, we state the hypothesis. Step 2, we state the level of significance. Step 3, we try to find the F calculated using the analysis of variance table. Step 4, we make decision, and step 5, we make conclusion based on our decision.